So as you see, there's a whole list of operations responsibilities. They include things such as fixing hardware and replacing software, applying patches and hot fixes, maintaining security, performing backups and doing recovery of those backups, media library. More importantly, down towards the bottom is variance detection. When do we have an incident? What exactly constitutes an infraction or an incident? How do we handle it when that does happen? And also perhaps some penetration testing so that we can identify where we're vulnerable and perhaps implement some mitigating countermeasures. Operation security involves protecting many types of components regarding your information systems, including the hardware, software, some telecom devices, even protecting your personnel in their daily activities. These are all parts of operation security. One of the first things we need to understand is what do we have to protect. Now, this was originally done when we performed our risk analysis and risk management processes. We identified what our valuable information assets were, and we quantified them, we qualified them, we evaluated them, we categorized them, and this helped us build our inventory of components. So based on that foundational work, we'll look at it now regarding the operation security aspects. These devices and components should all be documented, not just what we have, but where are they placed and how are they configured. Again, configuration management will come into play here. Our devices should be physically secured. We should have a secured server room, and we should restrict access. And anytime visitors are on the property, they should be well documented, they should be escorted, and not allowed to peruse and wander about at any point in time. Part of our operation security includes that we aren't in violation of software licensing. Many companies run into serious financial problems when they become audited by software companies and realize that they are hundreds of thousands of dollars in debt due to illegal software. There should be strict administrative policies regarding the installation of software. In addition, there are many operating system controls that can be put into place that disallow the average user from installing any software on the desktop computers. The company should utilize only their approved installers and or administrators for the installation of any software. An organization called ITIL, that's Information Technology Infrastructure Library, has a whole library of standards regarding information technology and the infrastructures. So this was a great resource as you are assembling your information systems as to how to securely implement those infrastructure components relative to your information systems. The ITIL standards specify some definitions for problem versus known error. A problem is something that is yet unknown and it causes incident. A known error is one that we've already identified. We may not have solved it yet, but we're working on its solution. These should be documented and should be implemented in controlling measures such as countermeasures. We should implement these into our standards, our baselines, and should be considered when we're placing security level agreements for device replacement and bringing systems back online. The objectives of problem management is to lower the impact of any problem. In other words, when the problem occurs, minimize or mitigate the impact of that problem. We want to reduce failures, and we want to prevent the same problem from reoccurring. In other words, solve the problem once, replace the faulty device, replace the faulty software, whatever it takes. These problems come from many different sources. They may be software, hardware, perhaps even environmental. So one of the first things we have to identify is how do we declare what a problem is? So we might consider that anything that is outside of our standard processing procedures should be a problem. It should trigger an investigation. Any incident that is unexplainable in nature or some random occurrence takes place, something we didn't expect, this is a problem and this should warrant an investigation. Back in the days of the mainframe, we had something called an initial program load or an IPL. These IPLs were where they would reboot the mainframe essentially. An unscheduled IPL was typically the indication of some kind of problem, and again should warrant an investigation. Very often this was done because someone installed a piece of software or some driver or other component that was unauthorized, and they were initializing that device or component, and this was generally an indication of some sort of malware or problem. And then any other sort of anomaly that occurs that we didn't expect, we should declare a problem and we should trigger an investigation. To summarize, anything unusual or unexplained, any deviations from standards, or any unscheduled IPLs, initial program loads, again, back in the mainframe days, these were all indications of problems and warranted an investigation. Non-employees should always be supervised and identified. There should be a specific reason that they're here, and only provide them access to the resources that they are here to access. As soon as they're done with their access, escort them off the property. Again, this is for their safety as well as for the protection of your valuable information assets. Some of the controls we have to put in place to reduce fraud and to improve the detection of fraud is the separation of duties. In other words, don't give one individual too much authority to allow them to violate our controls. If there's a sensitive process, break that process up into more than one person. In other words, in order for someone to violate our system and commit fraud, it now requires multiple people to be involved in the fraud. This is called collusion. When collusion becomes initiated, it makes the fraud much more detectable because people begin to make mistakes. They think somebody else took care of it, or they think somebody else didn't take care of it and they do it a second time and now it sticks out like a sore thumb. Very often people will feel guilty and may even confess to the fraud. So the more people involved in the fraud, the more likely it is to detect the fraud. Another component is job rotation. Allow the person in a job role for 60 days or 180 days and then require that they rotate out of that job. If they were committing fraud, the person that rolls into that role now will be able to identify that the numbers don't add up correctly and there has been some form of fraud being introduced. Always implement logging, and then of course you must monitor those logs. It's great to have very strict auditing in place, recording all sorts of information about what your users are doing. However, if you're not reviewing those audit logs, it's a waste of energy, it's a waste of resources. So the hard part of auditing and logging is someone must be formally assigned the responsibility for monitoring those audit logs. Only provide information on a need-to-know basis. Don't provide access to information if the users don't need the information. This follows an overriding principle that should be followed at all times, and that is the principle of least privilege. Anytime a level of access is being granted, always follow the principle of least privilege. This says give them only the minimum amount of privilege required for them to perform the required responsible tasks. Another form of controlling fraud is to require vacations. When a user is forced to leave for 2 weeks or 4 weeks to take their vacation, this means we have to put someone in that position, and this very often will identify any potential fraud that might be going on from that person that's now on vacation. Non-employees should always be supervised and identified. There should be a specific reason that they're here, and only provide them access to the resources that they are here to access. As soon as they're done with their access, escort them off the property. Again, this is for their safety as well as for the protection of your valuable information assets. A quick look at the security operations personnel, the types of responsibilities that this person has. They implement and maintain security devices and software. They provide security assessments. They maintain user profiles. Now, a user profile, and this was addressed in an earlier domain, is the collection of all resources and accesses that a user is provided regarding your information systems. So that's the user profile. It's the security administrator who creates this profile by granting access only on following the principle of least privilege. They maintain control of the access control mechanisms. They provide configuration control of all those devices. They implement the ACLs and the labels in a mandatory access control environment. They set the initial passwords for users, but then should require that the user change the password at first logon. The security administrator is also responsible for providing the review of audit logs, whether the administrator himself does it or he assigns it to someone else. This diagram summarizes those four processes. First, we have status accounting on the left, that it says, what is our current configuration? Identify the most vulnerable locations and the areas where attacks might occur. Document carefully how and why we might make changes and have a formal change control procedure. Very well documented, complete with approvals at every stage. And then the auditing branch simply monitors the change control process to ensure that the change we requested is the change and the only change that was implemented. Again, configuration management requires the consideration of security at each stage of the process and requires approval and review at each stage of the process. It should be thoroughly documented and validated that the change and only the desired change was implemented. So to summarize our change management program, first we have to put a program in place. We have to define what it is we need to manage. We will establish baselines relative to each component in our information systems. Some components are substantially more sensitive than others. So we have to establish and categorize these baselines of control and configuration management for these devices. And finally, we need to have procedures to implement the changes, the documentation of those changes, and then the review of those changes to ensure that the desired change and only the desired change was implemented in these sensitive infrastructure components. Next, we'll take a look at the protection of our media and other resources. Each company should have a media library where our media, such as CD-ROMs, DVDs, hard drives, tapes, and even printed documentation resides. It should be physically controlled and should be limited in access only through a specific librarian, someone assigned the specific responsibilities for this control. The media should only be provided upon approved and written request, and there should be documentation about information that was provided, or these components that are provided, what it contains, when it's expected back, and the authorized uses for these devices and other pieces of information systems. The hardware should be centrally located and physically controlled as indicated. The librarian should be responsible for all source software media. There should be rules on who is allowed to access it. In other words, a formal approval process and request process. And again, that process should include when does it get returned, what are the approved authorized uses for this media, and all the details that go along with this. The librarian is also responsible for maintaining the backup tapes, and that could be backup tapes that we keep on site, and we might actually keep backup tapes off site in case the building becomes destroyed or we lose access to the backup tapes here within the facility. There should be documentation of our configuration at the librarian, and this is also a fine place to control changes in that the configuration and changes to software, perhaps internally produced software. So again, a change control process should be in place for all of our internally created software. We see here that these labels should be including information such as when it was created, how long it should be retained, a classification level, who should be authorized to see this, who created it, when do we want to destroy it, and again, in some cases we may not want to destroy it, but we might want to just release it from its level of control because the information is no longer sensitive. Declassification, in other words. And then a label of what exactly this is and perhaps even a version number. All media should be managed using these following criteria. It should be marked, it should be logged. We should validate that the information hasn't been modified on the media. There should be physical access protection. In other words, we secure this media so that only authorized individuals are allowed to access the media. We need to protect it from environmental issues. If the rooms are too cold or too hot or the humidity is too high, that might destroy the media. We need to protect against these things. We also need to control the transference of this media amongst different localizations, perhaps different offices or even different departments. And then we also need to control how the information, how the media is eventually destroyed. Another aspect we need to consider is if we purchase third-party software, and very often these purchases are very expensive and require a great deal of time in customization and the development of the software to implement it and integrate it properly in our organizations. We've got huge investment into this third-party piece of software. What we'll generally want to do is require that the third-party software company provide a copy of the source code to an escrow agent. In other words, provide this source code to perhaps a lawyer that puts it in a safety deposit box just in case the third-party software company goes out of business. If they no longer are in business, we need access to the source code. Now, that third-party company doesn't want to give us the source code as long as they're functional. But if they ever go out of business, I'll need to hire programmers to maintain and modify this third-party software that we've spent so much in the development of. So again, a software escrow agent should be implemented in any major software purchase from a third-party company, so that if that company ever goes out of business, we now get access to the source code and we can maintain it over years and years going forward. Next, we'll look at object reuse, specifically media reuse. The reuse of media, especially magnetic media, has caused many exploits in confidentiality, integrity, and even availability. This has been a huge problem security-wise, so it has to be considered and addressed aggressively. The reuse of media very often exposes confidential information to unauthorized individuals. There are many ramifications of the exposure of this information. It can be a violation of state law and regulatory compliance issues, and can cost the company large fines. As we see here, several headlines related to the exposure of confidential information, very often through the theft or compromise of reused media. A fairly impressive statistic on this slide shows that 77% of all leakages were due to negligence on the part of employees. So very often, most of the time, when information is accidentally, quote unquote, leaked that should not be provided to the public, it was negligence on the behalf of our employees. It hasn't been from outsider attacks stealing the information, but negligence on our part. So, especially with magnetic media, object reuse is a huge vulnerability. We don't want to throw this media away. We spent money on it and it's still good, it's still usable. What we have to ensure, though, is that the media does not contain any residual information that might be compromised. There are many tools that allow me to reclaim deleted information off of hard drives that are reused and maybe even have been reformatted. I can still pick up a great deal of information off of these disks. The proper disposal of this should be very well documented and defined. At the end of the life cycle for a device or system, it should be very clearly identified how we will dispose of this. Generally, it should require physical destruction. For magnetic media, one approach is a degaussing system. This is a device that generates a very large magnetic field, so large that it overrules and overwrites any existing magnetic polarization that might exist. Now, this magnetic polarization on the magnetic media is actually the implementation of the data. And so if we can eliminate this polarization, we can eliminate 100% of the data. Another technology used to eliminate residual data is a process called zeroization. Zeroization is the process of overwriting the magnetic media with ones and zeros. Many different organizations prescribe different numbers of overwrites required to purge 100% of the data. With the use of an electron microscope, information can be read from as many as 7 times ago being overwritten. Another technology used to eliminate residual data is a process called zeroization. Zeroization is the process of overwriting the magnetic media with ones and zeros. Many different organizations prescribe different numbers of overwrites required to purge 100% of the data. With the use of an electron microscope, information can be read from as many as 7 times ago being overwritten. Many applications are available today to perform this zeroization process. As a matter of fact, there's a utility in the Microsoft operating system from as long ago as even NT4 called Cipher. Cipher is an application that overwrites all free space on a disk, first with zeros and then with ones, and then with a pattern of ones and zeros. So with running this application one time, you get 3 overwrites. In order to provide the number of overwrites required by NSA, we'd have to run this utility 3 times on the spindle to provide at least the 7 times overwrite. This would give us 9 overwrites and remove 100% of the data on the free space of the spindle. The Cipher utility only overwrites free space and does not overwrite your content. Other utilities overwrite 100% of the spindle and will destroy all data on the spindle. And probably the most certain form of removing residual data is the physical destruction of the magnetic media. You have to ensure that the destruction is complete, that a bad guy wouldn't be able to pick up a 10-foot section of a magnetic tape and be able to recover information off of that 10-foot span of magnetic tape. Here we see the definition for data remnants. Again, this is a piece of data that can be reconstructed after we've attempted to remove it from the media. There are many applications and forensics tools that can recover this information, even after we've deleted it and overwritten it. Purging, again, is the process of eliminating that residual information on the magnetic media. When a file gets deleted on a hard drive, the content of the file remains intact. It remains 100% available for recovery on the hard drive. When we delete a file, what happens is we actually only remove the first character in the table of contents for the partition. Every partition has this table of contents. In the FAT file system, this is the file allocation table. In an NTFS file system, this is called the master file table. And this is where the file system records the name and the location, along with many other attributes, of each file on the hard drive. As a file gets deleted, all we do is replace the first character of the file name with a question mark. This indicates to the file system that the space that this file was taking up is now free and available. The file system does not overwrite or remove the data from the magnetic media. It sits there in free space. Now, at some point in time, as you add content to the partition, that location might be written over top of. Now your data is gone. However, until that point in time, the information remains 100% available and recoverable. Reformatting of hard drives does not necessarily remove the content either. Reformatting the hard drive very often simply rewrites and recreates a blank master file table or file allocation table, that table of contents that we described earlier. So again, 100% of your information that was on the partition might still be available even after formatting. Mainframes have been around since the early days of computers. These were the very first computers. Very often they were very large, occupied whole rooms, perhaps even whole floors on buildings. There was a series of security concerns related to mainframes. One area is the unscheduled initial program loads, the IPLs. Another tool is called the Super Zapper. Super Zapper is an application that allowed the mainframe administrators to access any area of the operating system or content on the mainframe in violation of the access controls. So there are quite a few different tools available that, in the hands of a bad guy, can implement violations to the security of the mainframe systems. Next, we're going to take a look at backing up your data, your important information. There are several different types of backups. Most organizations use a combination of these types of backups. We have online backups. These are generally real-time or near real-time. In other words, as soon as the data is created, we get redundant copies of that data. This is generally done using a process called disk mirroring or disk shadowing. We also have offline backups that are done in a batch process, normally periodically, typically every evening or perhaps every 4 hours. There is a hierarchical storage process that we should be following. The hierarchical storage process provides us quick and immediate access to the information we use most regularly. Most current information resides on this very accessible media, very quick access times. But as this media ages or is identified as less critical to our moment-by-moment needs, we remove it from the more expensive immediate media and implement it or record it on more remote media, such as optical discs or tapes. Generally speaking, the higher we are on this hierarchical storage management pillar, the more expensive the media, but yet the more readily that information is available to us. The further down on this scale or spectrum in this hierarchical storage management process, the less expensive the media is, but the more remote, the longer it takes me to gain access to that information. We have these offline backups that we described earlier. These are a batch job, and they typically are generated once a day. Now we're going to look at the backup types. First, we're going to look at the full backup. When we identify what our valuable information assets are, we build something called the catalog. A catalog is a list of all files and folders that we want to have backed up on this remote storage media. We build the catalog and then we run the full backup. What the full backup does is it looks at every file that's listed in the catalog and it records that file to tape. It then resets the archive bit for every file it records. So at the end of the full backup, we have a backup of every file listed in the catalog, and every file listed in the catalog has the archive bit turned off. Now this is the longest backup to perform. It consumes the most amount of resources being the tape, the CPU, the RAM on the system, the performance of the system. These are all degraded during this backup, but this provides me 100% of the information I've identified as required for backup. Because I might not be able to afford the resources consumed by the full backup every single night, I will generally perform the full backup perhaps on a weekly basis and then perform smaller incremental backups each night. An incremental backup takes a look at all the files in the catalog, and only the files that are in the catalog that have the archive bit turned on get written to tape. Now, the way the archive bit gets turned on these files is someone has either modified the file, this turns on the archive bit, or this is a brand new file in this particular folder or on this volume. The archive bit identifies to the system that this file has not yet been recorded on any backup media. So when the archive bit is turned on, it's flagged as needing to be backed up. So the incremental backup again looks at all the files in the catalog, identifies the files in the catalog that have the archive bit turned on, and then just records those files to backup tape. Because all the files that have not been modified since the full backup are still on the full backup tape. I still have access to those original files. So again, the typical implementation would be a full backup once a week, perhaps every Friday night. But then on Monday, workers come in and perform their daily activities and modify or add files to the catalog. This is shown on the Monday indication here in yellow. So this represents the volume of files that were modified or added to the catalog on Monday. Now those files that are modified or new have not yet been backed up anywhere. We don't have a copy of that on any of our backup media. So Monday, when we run our incremental backup, what we do is look at 100% of the files in the catalog, and only the ones that have the archive bit turned on get put on backup tape. So as you see, the backup is substantially smaller and faster than the full backup that was performed on Friday night. At the end of the incremental backup, 100% of the archive bits are again turned off on all the files in the catalog, because we now have 100% of those backed up on removable media, the magnetic tapes. Tuesday rolls around, workers come in, they modify files yet again during their daily routines. So in the slide, Tuesday is identified in orange and shows a certain volume of content that has been modified from the catalog and needs to be backed up. Tuesday night we do the incremental backup and we record only the files that have been modified from the catalog. Those are the only ones that get written to tape. It's a short, sweet backup. Wednesday rolls around, same story, files get modified, and Wednesday night we perform the incremental backup. And again, at the end of the incremental backup, we turn off the A bit for all the files in the catalog. Thursday rolls around, and eventually Friday will roll around, and I'll perform a full backup all over again. So again, the incremental backup first only records to tape the content in the catalog that has been modified. This is flagged by the A bit being turned on. At the end of the incremental backup, we turn off the A bit for 100% of the files in the catalog. The problem is, while the backups are short and sweet and consuming the least amount of resources, the restore is problematic. The restore now requires each and every tape to be restored in the proper order in order to come to the point of the last backup. So the restore, where we've had a disaster, takes more time and more processing. Another alternative to the incremental backup is the differential backup. Again, I would always start with at least a weekly full backup so I get 100% of the catalog put on tape and all A bits are turned off on all those files. But then I would implement a differential backup throughout the week. We'll take a close look at how the differential backup works. As before, we perform a full backup every Friday night. 100% of the files in the catalog are backed up to tape, and I turn off the A bit in 100% of the files. Monday, workers come in and perform their daily activities and modify some of the files in the catalog, causing the A bit to turn on. Monday night, I'll run a differential backup. The differential backup looks at all the files in the catalog, and only the files that have the A bit turned on get backed up to tape. This is identical to the way incremental backups work, but here's the difference. Incremental backup toggles off the A bit when the incremental backup is complete. With the differential backup, the A bit is left on. So on Tuesday, when workers come in and modify files and add files to the catalog, not only are the Tuesday files have the A bits turned on, all of the Monday files also still have the A bit turned on. So when we run our differential backup on Tuesday night, I'm backing up all the files that were modified on Monday and on Tuesday. And I do not turn off the archive bit. On Wednesday, more files are modified, and the backup gets larger and larger as the days progress. So I'm now consuming more resources throughout the week, but what I'm doing is I am providing a much more rapid restore. So while my backups take a toll with the normal plus differential backup routine, my restores now only require 2 tapes. I need my full backup and I need my most recent differential backup because it has all the changes since the last full backup was performed. Another aspect of security with your backups has to do with protecting those backup tapes. These backup tapes are stored on site very often. They must be strongly secured. Very often they should be provided to the librarian, and only authorized individuals are allowed to access that media. This also lends itself very well to maintaining a solid inventory on that backup media. If I'm storing this backup media off-site, I now have the additional problem of ensuring that the off-site facility is securing my backup media properly, and only authorized individuals are allowed to access that. Further, periodically, you should perform a physical inspection of all the backup media to ensure that nothing has gone missing. Anytime a backup tape is gone or is missing, this is an incident and requires an investigation, because this could be a violation of confidentiality, integrity of your valuable information assets. Backups should always be encrypted, especially if we have sensitive data. As shown in these headlines, the loss of backup media costs many, many dollars and causes many, many problems, even here in the United States. As we begin to gain an understanding of what our critical information system components are, we need to identify two key terms or concepts related to those components. The first one is mean time between failures. This is a determination of how often we expect these components to fail. And the second concept is the maximum time to repair. That is the time that it takes to bring that system back online. So I need to understand these relative to these critical information system components. No matter what the device is, sooner or later it's going to fail. We need to find some way to get the system back up and running in the face of one of these device failures. One approach is redundant hardware, and in the case of hard disks, very often we have the capability to perform something called hot swapping, where I don't even need to power down the system. I simply pull the drive out and stick a new drive in while the system is up and running. We have other fault-tolerant technologies we'll be looking at shortly, but we also need to consider the concept of the service-level agreements. This is typically an agreement with either our own internal service department or an external service company that is going to guarantee how quickly they'll get our critical systems back online. So first, the mean time between failures, again, is a calculation or a determination of how often we expect these components to fail. Generally speaking, the more components there are in a system, the more likely one of those components is going to fail today, and we anticipate the failure more often. The next determination we need to make is the mean time to repair. Again, this is the average amount of time that it takes to get this system back online after a failure occurs. We compare the mean time to repair with our maximum tolerable downtime determination. This is the maximum amount of time we can live without this system or device functioning. And this then will dictate to us, perhaps we need to modify our repair procedure. We might need to purchase more fault-tolerant hardware or redundant hardware, or we need to improve the response time of our service level agreement with our internal or external service providers. We also need to analyze the single points of failure. This is a single component in a system that if it goes down, it brings the whole system down. We generally want to eliminate as many of these single points of failure as possible. Very often the way we do this is with redundancy. So the countermeasures for device failure is redundant LAN routes and WAN routes. Now these are for communications. Redundant and fault-tolerant technologies, we'll be looking at some of those momentarily. We should have a plan and documentation on how we deal with these failures, and our personnel needs to be very well trained on what to do in the face of one of these device failures. How to recognize it, what to do first, what to do second, and eventually how to provide complete recovery so that we're back in our normal operating state. Here we're looking at redundancy and fault tolerance for our computers and our disks. Hard disks tend to fail fairly readily, so this is one area that we'll be focusing on in this course. First, we start with disk mirroring and disk duplexing. Disk mirroring is where we have redundant hard drives that get the same drive letter. So when we tell the system to copy this file to the C drive, the system actually copies it to two different drives simultaneously because they both are labeled C. Disk duplexing is a hardware enhancement to disk mirroring. Disk duplexing adds a redundant disk controller, because with simple mirroring, even though I have two spindles, two physical hard drives, they generally are controlled on the same disk controller. If the disk controller fails, I can't access either of the spindles. We will look at redundant servers. We have network load balancing and we have cluster servers. These are two different levels of redundancy on our computer systems. This would satisfy our needs in the case of a power supply failure, a motherboard failure, or some other catastrophic failure on a complete computer system. We'll look at RAID, that's redundant array of independent disks. We have MAID, that is a massive array of inactive disks. And we have RATE, that is redundant array of independent tapes or tape drives. So these are some redundant technologies that we'll implement to provide an additional level of fault tolerance. We'll look at clustering. Again, this is a form of redundancy on servers. We'll look at backups. This is data backups. Some of them are real-time, some of them are not real-time, batch jobs. We'll look at redundancy in our networking, our backbones, so redundant backbones. We'll look at the difference between direct access storage and linear access storage. Direct access storage is the way a hard drive gets accessed. The armature can locate any position on the platters at any point in time versus linear access storage, which simply has to spool down the length of the tape to find the piece of data or information that we're looking for. We'll look at redundant power and redundant power supplies. And we'll look at redundancy in our networking paths with different networking topologies. Maybe perhaps using a mesh instead of a star, bus, or ring topology for our cabling. With disk mirroring, we write the same data to two independent disk drives. Typically, these two drives get labeled the same drive letter. And as a result, when the system, the operating system, receives the instruction to copy this file to the C drive, since there are two locations named C drive, the system copies the file to two specific, discrete hard drives. This way, if a single spindle fails, the other spindle, still labeled C:, is able to access the information. In this case, the disk controller is the single point of failure. If the disk controller fails, neither spindle is accessible. This slide shows the difference between disk mirroring with a single disk controller and disk duplexing, which is a hardware enhancement to disk mirroring by adding the redundancy of a second disk controller. This provides a higher level of fault tolerance. As I had indicated before, direct access storage devices are devices that don't need to be spooled, such as magnetic tape. They can be thumb drives or hard drives are typically the types of direct access storage devices that we'll bump into. We're also going to look at redundant array of independent disks, and this is referred to as RAID. Here we see 5 different RAID levels. Really, only 3 of these are ever used in the real world. We use RAID level 0, which is disk striping, great performance but no fault tolerance. We see RAID level 1, which is disk mirroring, and then we've already discussed the hardware enhancement to RAID 1, and that's called disk duplexing. That's redundant disk controllers as well. And then the third one that gets used a lot in the real world is RAID level 5. RAID level 5 is stripe set with parity. This takes the benefits of striping, which is great performance, but also adds fault tolerance to the stripe set. So let's look at these in greater detail. With RAID level 0, we have at least 2 and maybe as many as 32 spindles that we will array in a single logical disk. There will be up to 32 physical spindles, but we will array them in a single logical disk. And now what happens is I need to write a file that might be this long, and if I were going to write that file to a single spindle, it will take that much time. If I'm going to stripe this across, let's say 10 spindles, and I can write to those 10 spindles simultaneously, I will take 1/10 of the file and write it to each spindle simultaneously. So it has a huge performance benefit. In other words, for each spindle you add, you decrease the write time and the read time for this array. And the formula for this is 1 over n, n being the number of spindles in the stripe set. So if I have 10 spindles, I can read and write to this array in 1/10 the amount of time. Very high performance. This is the best performing of all RAID arrays. Now the problem with RAID level 0 is if any one spindle fails, you lose 100% of your data. This says that if you have a single spindle it is less likely to have a failure than the RAID level 0 with 10 spindles. That is 10 times more likely to fail today. So you're more likely to have a hardware failure with a RAID 0 array than on a single spindle. So again, great performance, no fault tolerance. As a matter of fact, it is even less fault tolerant than a single spindle altogether. You are more likely to lose data on a RAID level 0 array than on a single spindle. The next RAID level we're going to look at is RAID level 1. This is disk mirroring. And again, we've already discussed this pretty thoroughly. This is where I label two specific hard drives the same drive letter, so that when I tell the operating system write to the C drive, it has two locations labeled C drive, and it writes to both spindles simultaneously. If either spindle fails, the other spindle still is labeled C drive and still can access the information. So this provides a fine level of fault tolerance. I can lose one spindle and still receive or retrieve 100% of my data. The problem is this is the most expensive fault-tolerant disk array. The formula for the overhead on fault-tolerant disk arrays is 1 over n. In this case, n being the number of spindles, there are 2 spindles, and I lose 50% of my volume. So if I have 2 spindles with 1 gigabyte apiece of space, I lose 1/2 of that to the fault tolerance of the RAID level 1 mirroring. So I lose 50% of my volume to the fault tolerance. Again, highest level of overhead, but at the same time it provides me the fault tolerance. I can lose a single spindle. Mirroring does not provide either a performance boost or a performance benefit. RAID level 1 completes a read when the fastest of the 2 spindles completes the read. As soon as I have any one copy of this information in RAM, the read is complete. So I get a minor performance boost when I'm reading. Unfortunately, when I'm writing, the write is complete when the slowest of the 2 spindles completes the write. So in essence, the little boost and the little degradation that I might have in the difference in performance of these 2 spindles is negligible and offset by the other function. Now, RAID level 2, 3, and 4 are rarely used in the real world. RAID level 2 is bit level parity, RAID level 3 is byte level parity, and RAID level 4 is block level parity. These are generally not used in the real world, and we'll just mention them here. But now we'll step past them and go to RAID level 5, a very commonly used level of fault tolerance. RAID level 5 is stripe set with parity. This is where I get the benefits of the stripe set, the performance benefits, and I add to that an additional level of fault tolerance so that I can lose any one spindle and still be able to read and write to the disk array. So RAID level 5 has great performance, has a small amount of overhead. Remember, the overhead formula is 1 over n. So if I have 10 spindles in my RAID level 5, the cost of overhead is 1 over 10, or 1/10 of the volume of the RAID array is spent in the overhead for the fault tolerance. Another implementation that affords a level of fault tolerance for hard drives is called a massive array of inactive disks, or MAID. This is a relatively new in commercial use. This is where there's a large array of spindles, and we actually power down the spindles in between accesses to save their lifetime, extend their lifetime, and reduce power consumption. Again, this provides, because it's a large array, many different spindles, we can also add to that the fault tolerance of perhaps RAID 1 or RAID 5, and can add fault tolerance to the extended lifetime of the inactive disks, the spinning down of the drives when they're not being utilized. Next, we'll look at a redundant array of independent tapes, or tape drives. This is called RAID, and it's a similar concept. It uses arrays of tapes and tape drives to provide redundancy and fault tolerance on your backups. So again, it provides very high capacity, high data rates because I can write to these tape drives simultaneously, and it also affords a greater level of data integrity because I have fault tolerance on the tapes. I will add parity and even encryption to these backups. Next, we'll look at the controllers themselves. One of the earlier versions of disk controllers was called ATA, Advanced Technology Architecture, and this was used to connect IDE drives, relatively inexpensive disks, to a computer system. Now, the more expensive and higher performing controller is a SCSI controller. SCSI controllers are high performance and also higher dollar. They cost more. So to keep costs down, the extension of the ATA interface, the newer extension, is called the Serial ATA or SATA interfaces. SATA interfaces have higher performance and keep the cost down. These are very often used in the newer RAID arrays and MAID arrays. To extend the fault tolerance to more than just hard drives, we can look at the storage area networks, or SANs. Now, a SAN is a large server farm with large amounts of disk storage. These are generally connected to using high-speed networking communications between the clients that actually need access to the information and where the information is actually stored on the SAN. Many companies are able to afford their own SAN. These are very expensive because of all the high performance, fault tolerance, and redundancy that gets built into the SAN. Many companies can't afford it, so there are companies that actually lease SAN storage space. Now, what this requires, though, is that the company has to have high-speed connectivity to the internet so that they can access their SAN data very quickly and seamlessly. Again, let me stress that generally speaking, with a SAN, fault tolerance and redundancy and backups are all considered to be packaged inside the SAN. In other words, the SAN includes all these technologies. You've almost given up all responsibility for these features of fault tolerance and redundancy. So now let's look at redundancy on servers. There's generally two different types of redundancy on servers. We have network load balancing, typically used for stateless applications, and then we have cluster servers for stateful applications where we need to maintain state information for each connection. With a redundant server in either the NLB or the cluster server, if one server fails, the other servers in the cluster simply pick up the workload. In a cluster server array, the servers in the cluster are all aware of every connection that the failed server had, and one of those servers will pick up those connections and maintain those connections seamlessly to the end user. In the NLB cluster, these being stateless applications, there is no stateful information to record about any given session, and so when a client needs something else from this stateless application server, the server, one of the existing remaining servers, simply provides those services, and it doesn't really matter whether or not the original server is still online or not. Here we see redundancy at every level. We see redundancy at the firewall level, we see redundancy at the router level and at the switch level, we see redundancy at the application server level, and we see redundancy at the drive levels. Parallel to that, on the other side of the slide, we see redundancy at the network level, where we'll have redundant paths between our routers, so that if one router or one path fails, we have multiple paths to make those connections. In its truest form, we have the pure mesh. The pure mesh is actually more of an academic model than something we would truly implement in the real world. We wouldn't need this level of redundancy. For one thing, it costs too much, and typically our needs aren't quite this great. If I have 2 or even 3 paths to each router, this is generally sufficient. I don't need 5 or 6 or 7 different paths to each router. As I had indicated before, clustering is where we have redundancy on servers. Clustering typically is for stateful applications, and it requires additional hardware. Clustering is more expensive than NLB clustering. Clustering implies stateful application. It generally requires a private network for the members of the cluster for something called the heartbeat. The heartbeat is a signal that gets transmitted each second from one server to all other servers to identify the state of every current session that that server is maintaining. In the case that any server fails, all other servers in the cluster are well aware of every session that is currently being managed by the server that just fails, and it makes it seamless when one of the other servers picks up those sessions and can host those inbound sessions for the clients. The other form of clustering is called the network load balance cluster. And again, this is for stateless applications. Again, we don't need to maintain stateful information about these sessions, and as a result, it's relatively easy. The hardware requirements are substantially less for NLB clustering. One thing we always need to do relative to these systems is to back up our configuration files. In other words, have records of what the settings are, the configuration settings on each of these devices. These need to be stored somewhere securely, and you should have multiple copies of these in case that one storage space is a place that gets destroyed by the tornado or the fire or whatever catastrophe took out the devices that now need to be reconfigured. So what types of threats can affect our computer operations? By far, the vast majority of problems we have in computer operations deals with user errors and omissions. Simply users making mistakes. Oftentimes it's internal fraud. Someone is accessing information they're not supposed to. They are logging on in an unauthenticated manner. We might have system failures and network failures. We have malicious attacks from hackers. We have malicious attacks from viruses and worms. The reasons, the justification for these attacks could be espionage, could be financial or other forms of motivations for the bad guys to perform damage or do damage to my networks. So the second system recovery that we're going to look at is called the emergency system restart. In this case, there is a violation of the security of the operating system or the computer, and the computer recognizes this and actually performs a reboot all by itself. Now this is not a blue screen, but this is the reboot of the computer. In this case, again, no user interaction is required, as with the blue screen. The third system recovery is called the system cold restart. This is a system failure such as a computer lockup, where the computer stops responding to the user. And this is the one of the three where the user is required to reboot the computer manually. In other words, bend over and press the power button until the system shuts down. Give it about 5 seconds to let the capacitance bleed off of the system so that all of our buffer memories are now cleared, and then we power the system back up. This is again the one of the three that requires user intervention. So after a system crash, we should do a couple of things. First, the system failed for a reason. We need to find out why. So we enter into what's called single user mode. This is actually a simplified security state for the system, usually administrative level, and it allows me to interrogate log files, other types of initialization files that might lend some clues as to the nature of the failure. I'll identify what the failure is, I'll try to fix the problem that caused the failure, and then we'll revalidate the operating system, the applications, and other things, just in case this is a byproduct of some sort of attempted violation of the system. Perhaps a bad guy was trying to hack into the system. I need to validate that he has not been successful in any capacity. So what do we do to try and secure the systems? First, don't let users boot off of floppy drives or CD-ROMs or DVDs. They can violate your access controls and your security controls if they are able to boot onto their own media and boot into their own operating system. Users should not get access to the system logs, and everything they do should be logged. This should not be available to them to make adjustments to it. I need to be able to configure what I'm auditing and then know that I'm seeing 100% of what occurred without concerns that the user has scrubbed the logs or has somehow done something that didn't get audited correctly. Generally speaking, users should not be allowed to shut down systems. And here we're not talking about the user's workstation. We're talking more of our infrastructure systems. This again is why these devices should be physically secured, and only through strong authentication and restricted access controls should users be allowed to access these devices physically. Only my administrator should be able to touch the servers. And further, users should not be able to redirect output. What they might be able to access in view that is confidential, they should not be able to copy locally and put it on a thumb drive and take this secure confidential information away from the facility. So output from applications should not be able to be rerouted to anything other than what the program states, and that would be, again, our secure database. Next, we're going to look at some contingency planning techniques. So contingency planning says, what do we do when we have a disaster? What should we implement as an alternative to that primary system? So I'll look at backups and I'll look at recovery plans. I'll identify these mission critical functions and components, and then I will find ways to get them back online as quickly as possible through redundancy, through training, and through planning. We'll look at not just the critical systems themselves, but the things that those systems depend on. We'll be looking at power, AC power, air conditioning, everything that deals with keeping that system alive. Sometimes it's not so obvious. A printer is a useful thing, but it's not useful unless we have paper for it. So in this case, something as simple as a stack of paper could be the important thing to getting our reports produced. Contingency planning should include formal written procedures and training for the users that are going to need to implement those procedures. All users should be aware of when violations occur, know to recognize them, know to report them, and have some initial reaction to this disaster, this occurrence, this incident that may have occurred. Next, we're going to take a look at remote access. So next, we're going to look at some remote access security issues. Remote access is more and more popular these days as we have people telecommuting to the office. We also have remote access for branch office communications to the main office, and we also have remote access for our administrators that might need to perform some administrative functions at the office late at night or over the weekends. We've already seen a handful of details related to remote access. We saw Radius, remote authentication dial-in user services. We have TACACS Plus, which is Cisco's proprietary implementation of Radius, a dial-in standard. We have authentication mechanisms called Challenge Handshake Authentication Protocol, CHAP. We have the Extensible Authentication Protocol, which we've discussed in this course, and it was also discussed in other domains. We have Public Key Infrastructure, which is PKI digital certificates and asymmetric key pairs. We discussed two-factor authentication being stronger than single-factor authentication. Those factors are something you know, something you have, something you are, and a fourth component could be some place you are, and that place could be either logical or physical. Logical being address space or domain affiliation. Physical could be if you can't get into the room where the server is, you can't access that resource. And then finally we have token devices, which is a component of two-factor authentication. This is a device that you have to have that provides you the password, and then you also need a PIN to go along with the token device. This slide says a lot. This slide shows the way remote clients are able to connect into access corporate resources. Down at the bottom of the slide we see the client. Now in this diagram the client has two different paths that he can use to connect into the corporate network. The path to the left is where the client is using a dial-up modem and using analog telephone lines, and he dials into a RAS server or network access server. That network access server connects to a Radius server that provides authentication mechanisms to validate that this is a legitimate user and that he should be provided access to the network. That validation is done when the Radius server connects to the domain controller that stores the user database. Once that user is validated, then the dial-in server provides access to the corporate network for the user. The second path of access in this diagram is where the user, again down at the bottom of the slide, connects through a VPN server, perhaps through a dial-up or perhaps through his cable modem connection to the internet, and then builds a VPN to a VPN server on the corporate network. The VPN server again provides authentication services, usually using Radius, again, which connects to a user database. And once we validate the user's identity, we can provide access to the corporate network and the resources on the corporate network through the VPN. The benefit of the VPN is all communications between client and VPN server are encrypted because this channel is across public wires where bad guys could be monitoring our traffic. Always with remote access and dial-in, you want to implement these two features if possible. The first feature is called callback security. This is where the client dials in, authenticates, and then we hang up. We disconnect this client and call the client back. This does two things. First, it provides us a trail to follow in case the guy who dials in really is not an authenticated user, but has spoofed the authenticated user. This gives us a trail to follow to track him down. The second thing this does is, very often when a client is roaming, perhaps from a hotel or something like this, dialing in, the telephone charges might be as high as $1 or $2 a minute when he calls us. But when we call him back, we're calling him back using our corporate telephone system and our very low negotiated minute-by-minute rate. It might be the difference between $2 when he calls me per minute versus half a penny when I call him back. So callback security is a strong form of security with all dial-in services. The other component that we might implement is caller ID. Now, this is something that must be supported by your telco, and all your dial-in systems have to support this same caller ID service in order for this to work. But this again provides us true location, or at least telephone location, where the dialer is calling from. Other security measures that should be implemented relative to remote access are that authentication should never take place in clear text. Further, even our data flow probably should be encrypted. We should implement these VPNs using SSH, or VPNs such as IPsec or point-to-point tunneling protocol. And more often we're seeing the use of SSL so that our data flow and authentication processes are encrypted inside these tunnels. We should probably also configure our infrastructure systems to not be configurable via remote access. In other words, if the administrator can't physically get to the box cannot be reconfigured. Only our administrator should have access to these boxes or these infrastructure devices for reconfiguration. This is generally controlled using strong authentication and even physical access controls such as locked doors. Again, just like our server rooms should always remain within a locked and secured environment. Strong authentication includes the use of multi-factor authentication, and there are basically 4 flavors of multi-factor authentication. Something you know, something you have, something you are, and some place you are. Now that place could be a logical place or a physical place. Physical place be in the server room. Logical place is what IP address range are you coming to me from, or what domain affiliation are you coming to me from. So these would be those would be logical locations that we might implement strong authentication requirements on. Fax machines pose another form of security vulnerability. The original fax machines would receive an inbound fax and would actually print the fax right there on the spot and drop the sheet of paper into a hopper with 20 other faxes that have been received. Anyone who has physical access to this fax machine can peruse whatever is in the hopper and may be able to gain access to confidential and sensitive information. So these fax machines are generally not recommended when it comes to security considerations. The proper solution for inbound faxing is a fax server. This is a fax machine that doesn't print the faxes, but will actually reroute those faxes to the email mailbox of the intended recipient. This way, only after strong authentication can only the intended recipient access that document. It would be at their discretion then to print the document and maintain its security. So disable the print feature on your fax devices. Another component might be to implement an encryptor between 2 fax machines. Let's say we have a branch office and a main office. I can implement a fax encryptor on those 2 devices so that all faxes between those 2 endpoints would be encrypted at one end for transmission and then decrypted at the other end. Further, we want to implement logging and auditing on all activities with the fax machine. This could actually be a requirement through regulatory or legal requirements. To keep these systems functional, we also always need to consider the support systems or the dependencies that these systems have on the surrounding environment, such as heating, ventilation, and air conditioning. We need to provide good, clean electrical power and backup power in case of power failures. We need water and fire protection services, in other words, sprinkler systems, fire extinguishers, things along these lines. Our electronics generally should be contained within a humidity-controlled environment. Too high a humidity and we might get condensation on the circuit boards that are the electronics of the computers. This would cause arcing and corrosion. Too low a humidity and we get static electricity buildup and static discharge that can actually damage the devices. We want recirculating air conditioning so that we can filter this air and keep it filtered. We also want positive air pressure. That means we put more air into the room than we take out of the room, so that there's a constant pressure to push dirt and other debris out of the room. If we have negative pressure in any facility, any given room, that room will actually draw air in and also draw contaminants into the room. So we always want positive air pressure with filtered air so that we keep the air as clean and pure as possible. Next, we're going to move into vulnerability and penetration testing. Vulnerability testing is a huge project and should be very carefully planned out and agreed upon in writing before any action is ever taken in vulnerability testing. This is the type of test that, if you're not careful, will land you or wind you up in jail. So you have to be careful that you have very clear instructions on what you're allowed to do, what you are supposed to do, and who has authorized this particular vulnerability test. In essence, a vulnerability test, you try to break in. You try to find what you can steal. And these actions could wind you up in jail if you don't have proper documentation to prove that you are performing a legitimate test. So this agreement should be written and it should be signed by multiple high-level management that is authorized to implement this type of test or examination. Always identify to the company that there are potential ramifications of your vulnerability evaluation. You might accidentally cause a system to fail. You might break a window accidentally. It's not your intention to do these things, and you should always try to avoid doing any damage to these systems, but this is an invasive process. Damage can and very often will occur. So you will need a limiting of liability. In other words, warn them, I'll do my best not to break anything, but if anything gets broken, it's not my fault. You've agreed to this test and you recognize that there are some risks that go along with these vulnerability tests. You also need to advise the client that this is a single snapshot in time, that this test represents the state of security for their environment at this point in time. Tomorrow or the next day, when they have new employees or new services or new devices, this vulnerability test that we did today is no longer valid. We need to evaluate those new components, those new changes in the environment. We'll look at personnel. We'll look at the physical construct of the property as well. We also will then perform attacks and vulnerability assessments on the computer and information systems and networks. Many of the things we'll look at when we're looking at securing our environment and actually testing the vulnerabilities in our environment will include scanning the network, looking for other vulnerabilities, not necessarily network related, but physical access vulnerabilities, things along these lines. We'll look at the ease of cracking passwords. We should always be reviewing logs. Logs will show us where someone is trying to break into my network. We should look at the integrity of our operating system files. If a computer system gets compromised, very often the bad guy will insert a Trojan operating system file in the computer so that when the computer boots up, the operating system file as well as the backdoor or the Trojan also launches and provides this vulnerability so that the bad guy can break into the system again. Our systems should all include antivirus software. We should always probe all of the analog telephone lines and even digital telephone lines that are inbound into my organization. Very often we might be paying for 50 telephone lines, but we're really only using 40 of them because 10 of them have gotten forgotten due to personnel change and office changes and things along these lines. So I might have vulnerabilities in the telephone system that I'm unaware of. Then we should always be performing wireless surveying. War driving, perhaps if our facility is very large, I might need to use a car, but I should also do a walkthrough of the environment looking for rogue access points. I then will perform penetration testing of the network and operating systems on the computers in my information systems. And afterward, after I complete all these evaluations and tests, I always need to summarize, write a succinct report, and very often if I'm contracted to perform this level of action, I will make suggestions as to countermeasures that might help to secure their environment against some detected vulnerabilities. As I've indicated, with vulnerability testing, the first thing we do is recon. We figure out who the client is, where the vulnerabilities are, where the soft spots are. First, I'll implement passive recon, which is where I'm simply eavesdropping, I'm doing my homework, I'm looking at public websites to try and learn more about my target. Then I'll do active recon, where I'll be probing. Now, the more I probe, the more likely it is I'll be detected. So I want to be gentle about the probing. I want to hit the more public types of services provided by the company first. I'll hit their websites, I'll hit their FTP sites, and subtly and as discreetly as possible, I'll be learning and gathering information about the vulnerabilities or potential vulnerabilities on these systems. One tool that I might use is called SuperScan. This is a probing tool. Again, this tool can be detected. If there's an intrusion detection system in the target environment, this IDS might very likely pick up my probes. He may send up a red flag, or I still may fall below the noise level, and he's not going to send out an alert yet. So if I probe too aggressively, I'm more likely to trigger these alerts and draw attention to my probes. This is an example of another scanner. This guy has many, many tools to throw at the target. We can actually implement some mild forms of exploits to see if we might get away with a little bit of attack or actual penetration testing. So this tool provides a combination of scanning or probing as well as throwing some gentle exploits at the target. Another form of attack is the implementation of a keystroke logger. These are, in some cases, physical devices that connect between the keyboard and the computer itself. It's got buffer memory in there, and for every keystroke that the victim types, it records that keystroke. I later would then retrieve this physical device and would download it and then review the information that I find. And you'll find usernames and passwords and perhaps all sorts of other confidential types of information. There are also software versions of keyloggers. These very often are detected by antivirus software. So the good news is the more popular software keyboard loggers are identified and quarantined by most antivirus software. This doesn't mean they're not possible to be installed on your computers. However, it does mean that for the most part they are detected these days. So this would be the output from a keystroke logger. Another type of vulnerability testing is cracking passwords. Basically what I'm looking for here is I'm looking to identify weak or blank passwords. This would allow a bad guy to break into the network very easily. What I generally will use when I'm cracking passwords is either a dictionary attack or a brute force attack. A dictionary attack is a more predictable string of keys that users are more likely to use as their passwords. It might be a word out of the dictionary with a few numbers preceding and or a few numbers trailing the word. We may also use some routine substitution such as the number 0 in place of the letter O, or the number 1 in place of the letter I. So we perform these simple substitutions in a dictionary attack. And the dictionary attack can be implemented in a very short and abbreviated level, or it can be a more thorough dictionary attack, providing more variants of these dictionary words. Now, the dictionary attack is a subset of what's called the brute force attack. The brute force attack is exhaustive and complete. The brute force attack, given enough time, is guaranteed to crack that password. It uses every possible combination of characters to crack the password or to guess the password. So this guy is guaranteed to succeed, assuming he has enough time. So again, the dictionary attack is a subset of the brute force attack. The brute force attack is exhaustive. The dictionary attack is using more likely passwords. The brute force attack is every possible keystroke combination, trying to guess what the password is. The use of these tools should be eliminated or should be mandated as not legal on your network. This should be unacceptable use on the network. However, in the form of a vulnerability test, this might be the one time that these would be allowed. LoftCrack is a very popular tool that was around for about the last 10 to 15 years. LoftCrack was recently purchased by Symantec, but then it was dropped as a product due to peer pressure from the community. This tool, while it was designed for good intent, to identify weak passwords or to recover lost or forgotten passwords, bad guys use this tool to crack passwords and then log on in an unauthorized fashion on someone else's user account. War dialing is a tool used to dial every phone number within a given range. What should be done in a security audit is identify every telephone line that the company is paying for and then dial that number and see if you get a legitimate answer or if you get perhaps a modem that someone has forgotten and is still left available for a bad guy to break into. So war dialing will not only save money by identifying unused telephone lines that we can stop paying for, but it will also identify what we call hanging modems. And again, these hanging modems are a juicy target for an attacker. Phone Sweep is an example of a war dialing program. There are several others, but this application, again, will dial every number you tell it to dial and then try to identify the nature of the answer, whether it was a voice, whether it was a fax machine, whether it was an answering machine, whether it was a modem. If it finds an electronic device that is answering, it will interrogate that device to try and identify what type of device, maybe even what the manufacturer is, firmware versions, and then we can compile that information into a database of known vulnerabilities. Now I know how to attack that system. This is a sample output from a war dialing application. It presents a summary of successful calls to electronic devices and then would provide a report of what it thinks those devices are. The database, of course, will hold much more detailed information. Once I identify a target of interest, I can drill into the database and learn much more information about this particular device, again, lending itself to ease of attack. War driving is generally something we do through a city or a community looking for access points. However, from a vulnerability assessment perspective, I should be performing a wireless survey on A, B, and G frequencies so that I can identify any potential rogue access points. I may also identify where one of my neighbors has inadvertently set up an access point that is conflicting or interfering with one of my access points. In this case, I might send him a gentle or a friendly letter and identify that if he changes to channel 6 instead of 1, we would have much better wireless connectivity for our networks. This is an example of a wireless war driving application that is attached to a global positioning system. What you see is that it not only records access points, their MAC addresses, their channel numbers, their frequencies, the clients that are associated with them, it also plots their position on a map so that later I can go back to that location and begin to break into the juicier targets. This is an example of war chalking. As we indicated in an earlier domain, war chalking typically isn't done anymore. Back in the days when hacking was for the fun of it, for the challenge of it, war chalking was popular. It identified that somebody has found some information about a wireless access point and now is leaving his mark to publish the fact that there's a wireless access point here. These days, the incentive is more financial in nature. And if a bad guy can identify a vulnerable wireless access point, he's not going to tell anyone. As a matter of fact, what a bad guy will often do after he breaks in, implements his own backdoors, he will harden your system so that another bad guy can't compromise it and take away his new trophy. So a bad guy will break in, create his own backdoors, but then he will fix the security on your network. As we've indicated over and over again, wireless is one of your largest areas of vulnerabilities. We also saw earlier that 802.11, the original implementation, utilized a security protocol called WEP. WEP had vulnerability upon vulnerability. It had many, many weaknesses. Again, it used an improper implementation of the RC4 encryption algorithm. It used a way too short initialization vector. It didn't have any key rotation mechanisms. Every user in the cell used the same key for both authentication, and then that same key was the encryption key. And again, if a access point is using WEP as its security feature, WEP is very, very vulnerable, and this access point should be replaced. One of the standard security features on access points is MAC address filtering. It's very easy to identify an approved, acceptable MAC address on a wireless access point. All it takes is a simple sniffer on the wireless NIC, and we can identify what these MAC addresses are. Then, using a simple tool, I can clone that MAC address. In other words, place that approved MAC address on my NIC, so that that MAC address filter now will accept me as a legitimate client. Next, we're going to look at the actual penetration testing process itself. Again, this always starts with recon. I start with passive recon, where I am simply sniffing using a packet sniffer. I'm not detectable. I might be perusing their public websites using standard browsing tools. I might try to download some of their files from their FTP site. These are all passive recon types of tools. Basically, this is just doing your homework and understanding your target. Then we perform active recon. Again, with active recon, I'm actually starting to probe the client in a way that the client might even identify the fact that I am probing him. This might trigger intrusion detection and even intrusion protection devices to build up the defenses against my scans. Again, these systems can be configured to be very aggressive in their scanning or less aggressive, but that takes more time in the scanning. The less aggressive, the less likely it is to trigger the intrusion detection. So again, we perform recon. This is passive recon. Then we perform active recon, which is scanning. This is where I'm probing and I risk being identified. My next step, once I actively scan the client, I will be looking for specific vulnerabilities. Now I'll be throwing exploits at those determined or discovered vulnerabilities. The objective of these exploits is so that I can gain access to the system. This is unauthorized access. I've now broken into this system. Sometimes I'll even cause the system to fail. So this is one of those areas where, as I'm starting to throw exploits at a box, that box might fail. I gain access, and then I try to maintain access. So as soon as I gain access, I try to upload an agent so that this agent on reboot will also reinitialize. This is my backdoor into this system for ongoing access, unauthorized access to this system. So again, I start with passive recon, I probe, I scan, I identify the vulnerabilities. Then I throw exploits at those vulnerabilities until I gain access. Once I gain access, I upload an agent onto that box so that I can continue to maintain access. Now finally, I'll cover my tracks. I don't want anybody to know that I've been there. I'll scrub the logs. I'll even disable some auditing features. Also, if I'm good at what I'm doing, I will harden the box. Those vulnerabilities that I identified with the active scanning, if I'm good and I have my backdoors in place, I'll actually secure that box for the client so that another bad guy doesn't break into the box the same way I did and take the box away from me. So in addition to covering my tracks, I might even harden the system. So here we see a flow chart of how this process works. At the top on the left, we see the passive scanning. I try to learn as much as I can about the system through Google searches, through the search of Edgar. I might do NS lookups using DNS, and I'm just interrogating for readily available information. The client doesn't even know I'm looking at him. Then I move into the more active recon, where I'm actually probing the client. I'm running port scanners, I'm fingerprinting and footprinting the systems, trying to identify what systems are there so that I can begin to configure my attack on the vulnerabilities. Now, if the agreement with the client, this is the pen testing agreement with the client, allows me to actually penetrate, then I will start throwing my exploits at their systems. Very often, because of the risk of damage to their systems, they will disallow my throwing exploits at the systems. So in this case, I'd simply produce the report on the vulnerabilities that I've identified without ever violating any of their systems. If they have authorized me to actually perform the exploits, I now risk breaking some of their systems, but I will get much more detailed information about the nature of these vulnerabilities and a truer picture of exactly how vulnerable those systems may be. So here we go with the full summary. The first thing I do is passive recon. Once I understand who my client is, I then will perform active recon. Now the first level of active recon is footprinting. Footprinting is identifying, okay, I see 5 servers in their DMZ. There's an FTP server, HTTP server, and 3 SMTP servers. Then I start to probe those specific boxes themselves. I'm actually fingerprinting the boxes, looking for vulnerabilities. What operating system are they running? What patch level are they at? Are they missing any security patches? What applications are they running? Are those patched? Things along these lines. I'm now looking for specific vulnerabilities to exploit. Here is where I exploit. I now am throwing known exploits at the vulnerabilities that I identified during the fingerprinting mode. This is where I'm actually going to break stuff if the systems aren't stable. So this is where I might actually cause the system to fail, or this is where I actually take over a system. Now once I take over a system, I now can move deeper into their network and start to enumerate not just the DMZ devices, but actual intranet devices. So I'm now that I'm on a trusted system, I can now probe deeper into their private network, and I now will enumerate the resources that I can identify on their internal private network. Again, I need to exploit those systems as well with identification of known vulnerabilities and then the associated exploits that will penetrate those vulnerabilities. Once I have accessed a box, I've gained access to a system of desire, I now will try to escalate my privilege. Very often what I do to escalate privilege is I will cause a process to start that launches at a higher level of privilege than what I currently have from throwing my exploit at the box. Once this service or application begins based on this higher level of privilege, I now can exploit this new service and gain privilege level equal to the account that is used to launch this other service. Now that I pretty much own the box, I have free run on the box, I take whatever I care to. This is the pillage and the browsing stage. This is where I take whatever I care to, and I might even use this system as a launch point for a deeper attack into the network. So I can further expand my influence on this system of computers. And finally, I will cover my tracks, and I will also probably harden those systems so that some other bad guy doesn't find the same vulnerabilities and take those boxes away from me. There are several commercial grade penetration testing tools. One of the popular ones is called Canvas. On this particular graphic, what we see is the screen capture from Canvas. We show that the scan is in progress, and we also see the actions that the scan is taking. In the lower left-hand corner, what we see is a slider bar that adjusts from left to right, left being a very aggressive probe, very likely to trigger an intrusion detection system if one exists, but also one that's more likely to gain true information, as much information as possible about the target network. As we take that slider off to the right, we will issue a more passive or less aggressive probe of the target network. I may not gain all the information, it will take a substantially longer time, but it is notably more stealthy and less likely to be detected by some sort of intrusion detection or intrusion protection system. There are many, many different types of flaws and vulnerabilities that can be exploited within information systems. Flaws in the operating system kernel. Applications have buffer overflows. Symbolic links are paths to files that could violate or could bypass access controls. We have race conditions, we have ACLs that we can violate, Trojan applications, which is an application that looks to be for good cause, but actually has malicious software tucked inside of it that very often will open up a back door for a bad guy to break into, and then the Trojan will actually even call home and notify the bad guy that the back door is ready and available for the bad guy to break into. Now the last bullet is social engineering. Social engineering is where the penetration tester acts as an imposter, someone you should trust, perhaps an electrical repair person or a telephone repairman, and he convinces you to provide him access to resources that he should not be gaining access to. So in other words, he's a good liar. He convinces you to give him something that you should not be giving him. Another pen testing tool is called Core Impact. Core Impact is an impressive penetration testing tool that maintains a database of known vulnerabilities and has a database of exploits to throw at those vulnerabilities. It also includes agents that can be uploaded to the exploited systems so that your attack now begins at the exploited system, not from outside the firewall. So you can eventually work your way into where your agent is actually residing on the corporate intranet and your attack is from inside their firewalls. Finally, after the pen test is complete, we should produce a complete report. This report must be maintained with the highest level of confidentiality. You now are responsible for private information. If you've been able to break into any of the systems, if you've identified any vulnerabilities, if this report gets lost or stolen or leaked out, you now are responsible for any violations to those vulnerabilities. You should report on all gaps in current security controls. You should identify the capabilities of the IDS and IPS and give a complete picture as to the current status of security for the organization. Let's recognize again that this is simply a snapshot in time. This pen testing and vulnerability assessment should be performed on a regular basis. So here's a list of tests that we might perform in a vulnerability testing contract. We might look at scanning the network. We might look at ward dialing and ward driving. We look at antivirus applications to see if all systems have proper AV protection. We look at the logs to see if there are misconfigurations, if there are vulnerabilities, if there are attacks underway, if there have been attacks historically. We will also try to crack passwords, looking for blank or easy to crack passwords. We'll look at vulnerability scanning, which is scanning above and beyond the network itself, and we'll look at other penetration testing. Penetration testing generally implies the IT network. We then should also validate the integrity of all operating system files. If a bad guy has violated or compromised one of the computers, one of the first things he does is he uploads a Trojan system file. Now he uses a system file because it's required for the operating system to boot. In other words, his Trojan, his malware, is effective anytime the computer is powered on. So what I need to identify is that every operating system file that I'm currently running on is one of the correct and valid operating system files from the manufacturer of the operating system. The penetration testing contract will provide some information to some of the parties. Let's look at how those combinations lay down. In some cases, neither the IT staff is made aware of the pen test about to be taken place, and the contractor that's performing the pen test also is not provided any information about the nature of the network. They're both blind. We might call this a double-blind penetration test. In some cases, the attacker is provided a standard user account. Perhaps that's the nature of the inquisition by the company. They want to know if one of our users could actually hack into our database or some file server. So they might actually give the pen tester a standard user account and let the attacker use that account to launch his attack from. Sometimes the attacks are performed inside the company, behind the firewalls. Sometimes the attack is launched from outside the firewall. Be aware that today, in many cases, it is illegal to launch an attack from outside the firewall because you're actually utilizing the internet to perform your malicious attack. Even if the company authorizes this action, you're using the internet to do this, and the company can't authorize you to violate the rules of the internet. And we had already discussed the concept of single blind versus double blind on the testing. Single blind is where one entity has some information about the other entity. And the entities I'm talking about here are the IT staff, the network administrators, the security professionals on the corporate side, and the pen tester on the contractor side. So single blind, one of those two entities has some information about the opponent. In the case of the double blind, neither entity has provided any information about the ongoing penetration test. The IT staff is unaware that a test has even taken place, and the contractor is only given information as to who the target is and what hands-off servers might be. Many companies implement a tool called a honeypot. A honeypot is an enticement. This is a spoofed system. Very often it's a virtual machine, not even a real system, that has several known vulnerabilities. So if your company gets scanned by a potential attacker, one of the things he'll identify as a juicy target is this honeypot system. He will then focus his efforts on cracking into this honeypot system. Now this system, again, very often is not even a real system and should never contain any types of sensitive information. I might put spoofed information up there and let the bad guy think he just stole some database, but it's all bogus information. So in other words, I give the bad guy a juicy target to attack. He focuses his attention on the useless information that he gains from the honeypot. Meanwhile, he's leaving my legitimate systems alone. Again, this is an enticement. Now, subtle difference between enticement and entrapment. Enticement is simply providing this vulnerable system on the network. Entrapment would be my encouraging attackers to attack this honeypot. So if I were now to go on some of the hacker websites and identify my company as being a juicy target, that they don't know how to implement security, and we've found machines already that have vulnerabilities. If I compel attackers to come attack my system, this then is entrapment. In most cases, enticement is legal and can be prosecuted if a bad guy does attack. Entrapment is not legal, and the bad guys cannot be prosecuted if they attack. And finally, from a security standpoint, we should always be focused on monitoring the logs and auditing logs that we are collecting. If we aren't looking at all the activities that are going on, what's the point of all these logs? In some cases, there are third-party applications that will correlate these disconnected events, such as trouble tickets correlating to server failures and scans on other systems. And these might not be detected if we don't have a single point to pull these details together and analyze them collectively. We need to look at the big picture and pull together all the reports, all the event logs, all the audit logs, all the trouble tickets, and start to look for patterns as we analyze these various pieces of information that we have about the security of our corporate network.